Have you ever really thought about how they get those perfect, colorful stripes in your toothpaste? Or how they manage to get actual chunks of fruit into your yogurt without turning it all to mush? Well, the answer isn't some kind of magic trick. It's actually a piece of engineering, an unsung hero of the modern world that you probably interact with every single day and you don't even know it. The positive displacement pump. All right, so here's what we're going to dive into. First, we're going to pull back the curtain on this hidden industrial workhorse. Then, we'll get right inside a specific type, the twin screw pump, to see how it works. After that, we'll get into the real design puzzles that engineers have to solve. We'll also uncover a pretty surprising secret about what really makes these machines tick. And then, finally, we'll connect all of this back to the stuff you have in your own home. So, let's start with the big picture. Just how important is this so-called unsung hero? Well, to put it simply, it's the hidden workhorse that makes so much of our modern life even possible. Okay, let's go back to that question I asked at the start. How in the world do companies get those perfect little fruit pieces suspended so nicely in your yogurt? Or those clean, crisp stripes in your toothpaste? It seems simple, but it's not. The answer is a very specific and honestly, a very clever machine. And that machine is the positive displacement pump. Now, when you hear pump, you might think of something like a fire hose, a device that just uses raw speed to throw liquid around. This is totally different. This is all about precision. It actually traps a very specific fixed amount of fluid, then it gently moves it, and then pushes it out. The result is a constant, steady, predictable flow. And you have to understand, these are not flimsy, disposable machines. They are built to last. The American Petroleum Institute, for instance, has a standard, API 676, that says these pumps have to be designed for a minimum service life of 20 years. And get this, at least 3 of those years have to be completely uninterrupted operation. I mean, can you imagine that? A machine that's expected to just work nonstop for years on end? It's incredible. Okay, so we know they're tough and we know they're precise, but how do they actually work? To figure that out, let's go inside one of the most common and versatile designs out there, the twin screw pump. So take a look at this. The basic idea is just beautifully simple. You've got these 2 big screws that interlock with each other, and this is key, they never actually touch. As they spin, they create these perfectly sealed little pockets against the wall of the pump's casing. And that's where the fluid gets trapped right after it comes in through the inlet. So the fluid enters, the screws turn and trap it, and then that trapped fluid is just moved steadily down the length of the screws, and finally it's pushed out the other end. That's it. This really simple mechanical action is what creates that super smooth, non-pulsating flow, which is absolutely critical when you're handling delicate products that you don't want to crush or destroy. But it's never that simple, is it? In the real world, moving all sorts of different kinds of fluids presents a massive design puzzle for engineers. The biggest piece of that puzzle is something called viscosity, which is really just a fancy word for how thick a fluid is. So think about it. If you try to pump something really thin, like water, you run the risk of it leaking backwards through the tiny gaps between the screws. They call that slip, and it just kills your efficiency. But on the other hand, if you try to pump something super thick, like honey or molasses, you need a tremendous amount of force just to get it moving at all. And what happens when the fluid isn't just a liquid? What if it has solids in it, like that fruit puree we were talking about? Well, now engineers have a whole new problem: wear and tear. Abrasive little particles, like sugar crystals in a syrup, for example, can act like sandpaper and literally destroy the inside of a pump. The solution? Well, it's often to run the pump a lot slower and to use specially hardened materials for the screws to help them resist all that damage. Now, all of this, the viscosity, the solids, the wear and tear, it all leads us to a really fascinating and honestly a pretty counterintuitive engineering secret. It's all about why, in this specific world, torque is way more important than power. You would think, right, that to move really thick, heavy stuff, you just need a motor with a ton of horsepower. More power, more push. Makes sense. But you'd be wrong. As the experts at Alpha Laval put it right in their guidelines, the main consideration for picking a motor isn't power at all. It's torque, the actual rotational force. And this data table just lays it out perfectly. Look at the low-speed process line. That's when the pump is moving a really thick product. It actually requires very little power, only about 4.8 kilowatts. But look at the torque. It needs a massive 226 Newton meters of turning force. Now compare that to the high-speed cleaning cycle at the bottom. It uses more than double the power, but it needs less than half the torque just to keep those screws spinning. It's crazy, right? So what's the big takeaway here? It's that getting a thick, gloopy fluid to start moving from a dead stop requires an immense amount of initial turning force. It's kind of like trying to turn a big, rusty bolt with a wrench. You don't need speed, you need that raw, brute rotational force. And that, right there, is why in the world of pumps, torque is king. Okay, so let's bring all this home. For this last part, let's see exactly how all of this complex engineering actually shows up in your day-to-day life, from the things in your kitchen cabinet to what's on your bathroom shelf. So next time you're in the dairy aisle, just stop and think about this for a second. That super creamy stirred yogurt you love, it needs incredibly gentle handling so its texture doesn't get ruined. That block of cream cheese? That's a high viscosity nightmare that requires huge amounts of torque to even get it to flow. And the yogurt with fruit pieces? Well, that's that solids handling challenge we were just talking about, trying not to damage the goods. And it's the exact same story over in the beverage aisle. You got juice with pulp? That's the challenge of pumping solids that are suspended in a really thin liquid. All those sugary beverage syrups, they can be super abrasive, which means you need those specially hardened screws to stop them from getting worn down. And finally, let's head back to the bathroom. Toothpaste is probably one of the most difficult things to pump, period. It has an insanely high viscosity, and it basically refuses to flow on its own. It's the ultimate pumping challenge. And just like with soaps and gels, it's a job that can only be handled by these incredibly versatile and precise machines. So there you have it. From the food on your table to maybe even the fuel in your car, the positive displacement pump is a true invisible engine of our modern world. It's just a perfect example of incredibly complex engineering that's hidden in plain sight. And it really makes you wonder, doesn't it? What other hidden machines, what other unsung heroes are quietly powering your life every single day?